The purpose of our engineering project is to create a public access at the McKeever Landing Canoe Park that will allow visitors to more safely and easily transport canoes and kayaks, as well as themselves, into and out of the deep river.
Our final design solution consists of the following parts: a wooden ramp extended to the edge of the cliff with wooden collapsible parts connected to the main beams with a galvanized steel axle. A two-crank system, one used for transporting the canoe and the other used for pulling up the collapsible extensions. A hollow plastic flotation device attached between the extensions. Within this flotation device allows the ramp to adjust to the water level. A wooden staircase with a handrail as well as a galvanized metal ladder extension attached to the end of the staircase to allow users to safely enter and exit the river despite varying water levels. For our design, we selected the wood to be white oak owing to its high durability and water resistance. Additionally, white oak is very cost effective and easy to work with. Ensuring that the metal components of our design are galvanized helps them resist corrosion.
In our final prototype, due to time constraints, we focused on constructing only a quarter-scale model of the ramp, and due to material constraints, we had to make a few adjustments. First, we substituted white oak with poplar wood because white oak was not available in the right dimensions. And secondly, we substituted the steel axles with scaled-down 3D printed plastic ones. And lastly, we substituted the plastic flotation device with a foam block of scaled-down dimensions.
We came up with different user scenarios to explain how our system functions in various situations. In a typical scenario for launching the canoe, the ramp would already be deployed and the user would slide their canoe down the ramp into the water. Then, in order to retrieve it, the user would tether the canoe to an anchor point, go up the stairs, bring down the hook for the boat crank, and then retract the boat crank, then detach the canoe at the top of the ramp. And in the case of flooding or other extreme weather conditions, the collapsible extension of the ramp would be folded up. The extension should be folded down before the next use.
Our design criteria targeted safety, cost, manufacturability, ease of use, weight capacity, efficiency, durability, and environmental impact. Our prototype met the design criteria for cost, which is $5,000. We calculated the total cost of materials used for building the final prototype to be $780. Our prototype also met the design criteria for environmental impact, which is achieving a risk level of 10 or lower. Taking into consideration different impacts the installation of our system could have on the surrounding environment, we calculated the risk level to be 8. Our prototype also met the design criteria for manufacturability. We took 10 hours to assemble a quarter-scale model of our design, and based on this time, we predict that the construction and installation of the full-scale model will take more than 10 hours but less than 50, which is a target value for manufacturability. However, we would only have an accurate measure of manufacturability after we actually build and install this full-scale model. Testing for efficiency was done by measuring the time it took for a volunteer to launch a canoe with our quarter-scale model. It took about 18 seconds for the canoe to be launched, which met our design criteria. However, more accurate testing will have to be done with the full-scale model since the ramp will be longer, the canoe will be heavier, and different users with different strengths will be using the system. Weight capacity was tested by modeling our canoe ramp design on SolidWorks, which is a computer-aided design program that allows users to test the maximum stress or weight that a structure can withstand. We found that our ramp is capable of supporting 300 pounds, which meets our design criteria. We were also able to make conclusions about the safety design criteria, since safety of users may be impacted when the maximum stress capacity is exceeded. Since the ramp meets the design criteria for weight capacity, we concluded that the requirements for safety were met too. We can further test safety by first installing the full-scale model and keeping record of how many injuries occur while using the ramp over a year. Lastly, we concluded that requirements for durability were achieved based on SolidWorks 2, since we thought that one of the only situations that could impact the durability of the structure was the ramp collapsing under weight. We can further test durability by keeping track of the product lifetime of the installed model.
Our solution needs to be constructed and installed as a full-scale model at the actual site, with stairs included. In addition, the design criteria can be more effectively tested once the full-scale model is installed and used in real time. In particular, efficiency and ease of use need to be further tested.